That good? Yeah. Okay, good afternoon, everyone. My name is Jessica Copeland. I'm a first-year PhD student at the University of Hertfordshire, and my supervisor is Ben Birmingham. Today, I'll be discussing the work I've been doing to investigate the atmosphere of the cool T9 brown dwarf WISE 0751. So the overview of this talk, I'll start with an introduction to WISE 0751 and a little bit about the wider sample, and then the retrievals I've performed on the atmosphere, and then finally I'll discuss the explorations on the limits of detecting deuterated methane in the atmosphere. So observations of W0751 were part of the JWST Geo 2124 proposal. So observations of the whole sample were taken with near-spec MIRI in these filters. And these were chosen because they were 12 objects that shared a similar mid-infrared color, but showed marked differences in their 4.5 absolute magnitudes. So it was kind of showcasing the diversity of Jupiter-like atmospheres. So I carried out retrievals specifically using the observed spectrum in the G395H. So we've seen this plot already. So as we can see, it's a little bit of an outlier compared to some of the other ones. It's underluminous. And so we've got some others from the wider sample that we've also heard about and have been published about already. So this is the G395H spectrum. We've got the actual spectrum plotted in black. There is the 1 sigma also plotted on there in red. It's very hard to see, and that's thanks to the really high resolution of approximately 3000. And then our yellow is the maximum likelihood spectrum produced by a clear atmosphere retrieval. So we can see it loses it a little bit in certain areas, but overall it's reasonable quality. So WISE 0751 got a bit of a history. So it was discovered in 2011 and originally deemed a field dwarf and classified as a T9. Then it was suggested to be a subdwarf, and it showed some quite unusual observations in terms of color. And then most recently, there's the discovery that it was in fact a bound companion. So that's independently discovered. And so we've labeled it as a planet, and it's got a couple of new names. So Coconuts 2b with an excellent acronym. So there we go. So the system lies about 10 parsecs away from us. We've got our host star, which is L3426. It's an M3V dwarf. And then about 6,471 AU away, we've got W0751. So very wide orbit. And we can see in our image here, that is W0751, and the host star is too far away to be in the image. Its host is thought to be young, thanks to its activity. And so there's been debate about whether W0751 is also young. It won't have formed in situ where it is. So there's a bit of debate about the history of the system. So in terms of expectations and questions about the atmosphere, so we're expecting a strong presence of water, methane, and ammonia. We may expect an adiabatic thermal profile in the deeper atmosphere as we get into the convective zone. It might be cool enough for a cloudy atmosphere, and there may be the presence of deuterated methane. So I performed my retrievals using Brewster. So I take my data and I set my parameter ranges, and those are for things like the gas abundances, any clouds, and the thermal profile. I then use MC to select parameter priors, and those go into the forward model to go through the thermal profile. We take opacity and scattering, radio transfer solver, and produce a synthetic spectrum, which we then compare to the real spectrum. The retrieval framework makes adjustments, and we repeat the process until we've got our maximum likelihood, and we output our posterior samples and our BIC values for comparison of models later. So the first retrieval was for a clear atmosphere, so cloud-free. Not in chemical equilibrium. Here we're using vertical mixing ratios. On the right, we can see the gases we've chosen. So these are things that we're expecting in this temperature regime. And we chose a relatively free temperature profile. So it's a 13-point interpolator spline with smoothing via penalization on the likelihood. And that is an almost direct adaptation from line 2015. So here we see the pressure temperature profile. So this describes how the temperature changes through depth in the atmosphere, where pressure is acting as proxy for depth. Our black line in the middle is our profile. Our dashed lines are condensation curves. So these are curves where these gases could condense, but not that they must condense. So it depends on certain conditions. And then our solid color lines coming through are our Sonora Bobcat models for 3 different temperature regimes. And then our red shaded zones are the 1 sigma and 2 sigma variation. So we can see it's not showing as adiabatic in the deeper atmosphere, and we're actually verging on isothermal. So we're looking for an explanation of that. So the first idea may be cloud, but before we get to that, discuss our retrieved gas abundances. So we can see that, yes, we are seeing water and methane, and our methane is dominating over our CO and CO2. And we're getting a very low value of deuterated methane and a very low value of phosphine. In terms of retrieved bulk properties, we get a low metallicity and a high CO ratio. And our mass, I mean, it's coming in a brown dwarf, but those errors are very wide, so could equally be planetary. So the next thing to do is to introduce a cloud. So in Brewster, you could choose a gray cloud, a power law cloud, or a me-scattering cloud, and then physically a slab cloud or a deck cloud. So here we've chosen a power law deck cloud, and everything else stays the same. So a power law cloud has opacity depending on wavelength, according to this. So tau equals tau 0, lambda to alpha. So alpha is our cloud index. And then a deck cloud has opacity increasing with pressure. So the location of the bottom of the cloud is actually unknown to us. So we have to add these parameters at the bottom into our retrieval and set new priors on them. So this is the resulting pressure temperature plot and location of our cloud. So as we can see, that doesn't fix it. It puts our power deck very deep into the atmosphere, and we're still seeing that isothermal behavior, albeit with a bit more wiggle. So there must be something else going on. We're not sure what yet. The next thing we might try is a me-scattering cloud. That red line there is for ADP, and that seems to be the closest thing. So might try that. So we'll leave that there for now. And we'll move on to detecting deuterium. So going back, that value of -7.77 is not well constrained. So in a brown dwarf, we expect not to see deuterium because we have expected to have burnt it away. And we would like to know whether there's actually no deuterium there or whether we're not sensitive enough to it. So the way we did that was to simulate having a Jovian abundance. So from the Jovian D to H ratio, took a percentage Jovian deuterium abundance, converted that into a deuterated methane abundance, replaced that into our state vector, generated a new spectrum from our forward model, simulated Gaussian noise using observed error, and then performed the clear atmosphere retrieval again. So with 100% Jovian abundance, our input value was minus 4.35, and we can retrieve that. With 10% Jovian abundance, it's minus 5.35, and we can also retrieve that within our error bars. So the question is, if we go down to 1%, are we still retrieving that? We'd like to know where the limit of Brewster's capabilities are in that respect. Or is there really no deuterium there, in which case, has it all burnt away? So in conclusion, the spectrum from JWST is excellent, a great resolution. There are questions about some of the properties we've been retrieving and about that deuterium abundance. And all I can say is keep an eye out for the things coming down the line. So there's another proposal that will be taking more observations which will increase resolution. And there's also work to do with SED fitting for other properties. Thank you.
So, when you decided to add a file, did you only red flag and
it's pretty much only in the pre-T profile. Mm-hmm. There are a couple of things we've got on a list to try next, which I haven't mentioned because we haven't explored them quite yet. Mm-hmm.
Really nice slide. And I see that the retrieved TV profiles seem to have a pretty broad distribution as compared to the, I mean, my impression about the typical signal-noise ratio of the James Webb data. Can you add some thoughts?
So it's tightest around the central values, and it does widen out around the top and the bottom, and it is kind of expected. It's just exploring more prior space up there, and it's the potential that actually those aren't the real locations of the PT profile at the top and the bottom, like it could be anywhere within that distribution. So top and bottom we treat with a pinch of salt, and actually where it's really tight in the middle is where we trust it, as it were. But that's where our inflection point is coming in for our unusual behavior.
I mean the TP of the next.
Oh, sorry. Yeah. It's a bit wiggly. Yeah, this is, in terms of the BIC as well, this is not preferred. It's still preferring the clear atmosphere at this point. Yeah.
Okay.
Oh. Don't want to steal it.
Yeah.
We're going to talk about
Can everyone hear me? Okay,